Okay, what I wanted to talk about in this short video, and this will actually set up a couple of the problems I'll do, is how to compute the cross-sectional properties of composite sections with something like Excel or a spreadsheet. There's lots of ways you can do it, but I'll show you. This actually becomes the most tedious thing about this is you have various types of channels. Maybe they have little details on them, and you have to compute in general the centroidal locations so you can determine the neutral axis, and then you actually will need to be able to compute the second area moments around those axes. Okay? Also, I won't talk about, but then if you're doing transverse shear, it would be nice actually also to be able to compute. I should probably add this on the spreadsheet, but it doesn't do it yet. But to basically be able at least to compute the Q value, at least to the neutral axis, to give you the transverse shear stress. All right. So what you find typically is, we invoke combinations of parallel axis theorem with, breaking these sections up into, their own regions, and using that to compute the location of the centroid and the area moments. Like I just said, it can be a kind of a tedious process. It's definitely an error-prone process. So what I wanted to kind of look at was a spreadsheet. Obviously you can't really use this on exams typically, but this is something that you can kind of keep with you and use over your careers. And also it's a good approach for other things that are very similar in nature. You'll find this in other disciplines that you'll have repetitive tasks to compute, and then setting up simple spreadsheets are easy ways to do it. All right. So here's an example of this spreadsheet. Okay, so this is one that I set up. It has up here a couple of different definitions for simple sections. So here I've got box, which I really should call a rectangle, and then a tube. All right. So by box, I mean really a rectangle, and it's given a base and a height, and that defines the box. And then also I talk about a tube, which has two values, an outer diameter and an inner diameter, and then obviously by setting the inner diameter to 0, you get a solid cross-section. So the first part of the spreadsheet, these lines up here, let you put in those dimensions, B and H, and then what it spits out. So in general for this spreadsheet, the blue sections are where you have to input. So you can change the base from 5 to 2, and it affects the rest of the spreadsheet. The height you can change from whatever this is, 1/8 to 3/16 to let's make it like 5 or something. All right, and what does it give you? The rest of this stuff is what it calculates out. So C1 and C2 are the outer fiber distances from the centroid. Okay, so you go from the centroid of this shape, and obviously you go down 2.5 units, that's the lower fiber, and up 2.5 units, that's the upper fiber. It also will compute the cross-sectional area, and then it'll compute the eyes about the z-axis and the y-axis. And so I didn't quite label it here, but basically, if we go back to this section, I'm calling this the z-axis and this the y-axis. So the eye about the z-axis is the base times the height cubed on 12, and the I about the y-axis is the base cubed times the height about 12. Okay? And I didn't do it, but I should also put J. We can do J, because J is actually just equal to the sum of the X and Y area moments. So I can actually do that. Compute J for all these as well. All right. This is the same thing, just doing the same operations, but for a tube. Okay. So you can insert rows and add other composite sections, right? These are the primary sort of base cross-sectional areas, the fundamental geometric shapes that you use. And then we're going to add them together down in this portion to get the total properties, okay? So again, the big things we're going to get are the location of the centroid. It also will compute the total area of the composite section. And then it'll get you the I. And now here I'm just talking about the I about the neutral axis. This is really the IY. About the neutral axis, and then the outer fiber distance from the neutral axis. And also I'm computing the shape factor, which is the I over the maximum C1 or C2, and then also the shape function. Just the shape factor divided by the cross-sectional area. So this at least gives you a number that you can compare effectiveness strength to weight ratios. Okay, because remember the strength is proportional to S, and the weight is going to be proportional to cross-sectional area. So looking at S over A gives you basically a number that kind of speaks to the effectiveness of the cross-section to carry load versus its weight. All right, so how do we do this? This is, like I said, this third block here is what does the composite body analysis. So here, this picture here pretty much explains what the columns are. This one has 3 elements. Basically, the section I did here was one we did in one book. This is I forget the actual dimensions. I look it up. We have a solid tube and then a thin web that comes up, and then a hollow tube on top. Okay, so we have 3 shapes. I forget which I call what. Let's see what I call what. Shape 1 is the web. I know you can't see this. I'm writing it down. So basically I'm calling this web section 1, the bottom solid tube section 3, and the top hollow tube section 2. All right, so that would be the example that I'm showing here. Now the parameters that we put in there or into the spreadsheet are as follows, right? So if you look at this, this is a general illustration. Here we have 2 sections. They're both rectangles, section 1 and section 2, and they're going to add together to give this composite L section. So the first column we are going to add in here, this YB. Okay, so this is the distance from some reference, some datum, to the bottom of the shape. So this is YB for the first shape, and this is YB for the second shape. All right, that's YB. You put that in. Then you have to put in the C1s. So that's the distance from the centroid down to this edge. Okay? So we keep the negative signs. These are basically what are copied from here. So here's C1, for example, is the distance from the centroid down to this edge. Or actually, I should say the distance from the edge to the centroid. So that has the minus sign. And then the C2 is the distance from the centroid to the top edge. Okay, so you need that to compute the C's for the section. Then obviously we input the area for the section, and again that just gets cut and pasted from up here, and also the I, and this is going to be the IY. I'm sorry, the I about the Z-axis for that section. All right, we do this for the 3 shapes. Then the rest of it is what calculates the property. So here you get the location of the centroid of each shape. Here it gets the area of each shape multiplied by that centroid arm. All right, adds those together divides that by the total area, and that gives me the location of the centroid. Right? The distance from this datum to the neutral axis. That's this yellow value here, YC. All right. Then it also does parallel axis and adds up the shapes and gives you the I about the neutral axis, and then the distance from the neutral axis down to the bottom edge, and then also up to the top edge. Okay, these are the two C's. Then knowing that, you can compute the shape factor, and then of course the shape factor divided by the cross-sectional area. So that's the way it works. So here I did an I-beam. So I just copied the page and I do an I-beam, and actually I put some parameters up here to deal with the I-beam. So let's see if I can get the, what did I do for, this is how I define the geometry of the I-beam. Let me get another piece of paper. So here's an I-beam. All right, let's see what I used as the variables. So W is the width of the I-beam. Maybe I could just do this. Yeah, that works. W is the width of the I-beam. So that's W. H is the height of the I-beam. That's the total height of the I-beam. TW is the thickness of the web. And then TF is the thickness of the flange. And for this one, we assume that the flanges have the same thickness, okay? So it doesn't allow you to deal with different flange thicknesses. Okay, so the way we do the analysis on this section is we break this up into 3 boxes, right? So I'm going to call this shape 1. The web is shape 2, and then the top flange is shape 3. All right? So here I've just put in those values. And then, so for example, for the first box, for shape 1, the base is equal to the width of the flange. So I just kind of set that up as a referencing that cell. So, in fact, when I change this value, change it to 6, it changes this automatically and updates all the other calculations. So we change it back to 5. All right, the height is obviously going to be the width of the flange thickness. And so that's what we have, flange thickness. The second shape is the web. So the web has the base of the web thickness. And the height is now the total height minus 2 times the flange thickness, right? This height of this is the total height minus 2 times the flange thickness. And then lastly, for the top flange, it has the same, I set it up the same way as the bottom flange. Actually, I don't really need to have the second flange calculated, but I guess I could. I guess if you want to make different flange thicknesses, you can go in here and modify this, but it would screw up a little bit like this calculation, but you got to be careful about it. I don't really use a tube, so that's gone there. Okay, so now once I do that, all right, so I'm sorry, so where was I? So now we have to use the 3 shapes together to get the composite shape properties. So I have the 3 boxes, and I guess I could give them a little better names. This box here, come on, is really the lower flange. This is the web. And this is the upper flange. All right. So I can probably just give these guys their names here. Okay. So the big thing, these C1, C2, and A and I's, these all get copied right from up here. Okay, so you can actually copy them by hand, or I tend to kind of do a cell reference. So there you see that's the C1 from there. So as that updates from this calculation, it updates here. And likewise, that's the C2. That's the area. And here's the I. So it's important we get the IZ, not the IY, the IZ, right? We're not really doing calculations out of the plane. If you want to rotate the section, you can do it through another spreadsheet. And the same way goes with this. So all these are really just cut and pastes from up here. And you can see actually the way it's set up, so I can just cut this whole row and it goes right here. All right. Okay. YB is what kind of gives the orientation to those sections to compute the parallel axis theorem properties. So if we go back, now I'm going to call the reference here right to this bottom edge. So actually YB for section 1 is 0. Now YB for section 2 is this distance, right? That's the flange height, right? So you can see it's the flange height. And then the YB distance from the datum to the base for the third section is the flange height plus the web height. So I think I probably put that as an equation, maybe if I was smart. Oh, I think I did a different one. I did it as the total height minus the flange height, same difference, okay? So basically, I set up all the equations in here, so if I change this, it'll affect all these other blue regions. So now once we get YB put into here correctly, the locations of the base point from the datum, it can then compute, well obviously the area of the total section is easy, that's just the sum of those. Here is the location of the centroid with respect to the datum. So you can see that's basically going up to YB and then subtracting off this outer fiber distance because it has a negative value, so then going up that distance. Okay, so this is the distance from the base to half of the flange, and you can see that is 1/2 of this. Here's the distance from the datum to the center of the web, and here's the distance from the datum to the upper flange. This is the product of the area times that centroidal distance. That's the numerator of the equation to find the centroid. That's the first area moment. We sum those together. This is the total product of AY, A times Y for each section. Now when you take this product divided by the total area, right? Here's the sum, right? That gives me the location of the centroid from the datum plane. So that's saying the location of the centroid of this I-beam is 5 inches up, which should make sense because the total height of the beam is 10. So obviously it's 5, right? But this does it for general sections, right? All right. Now that we know the centroidal axis, we can get the distance from the neutral axis, right? This is actually the neutral axis location. Once you get the distance from the neutral axis to the centroid of each shape, right? This distance, right? So this is YC for the first body, the second body, and the third body. Okay. Then we can compute I about the neutral axis for that shape by invoking parallel axis theorem, right? It's the I plus the area times this distance squared. So this is just the parallel axis calculation. This is I for each shape using parallel axis. We sum it up, that gives me the total I. Likewise, we compute the distance from the neutral axis to the outer point of the shape, and then the actual C1 is the minimum, and the C2 is the maximum of all these numbers. So that's the greatest distance from the neutral axis to the biggest outer fiber, right? So this is the distance from the neutral axis to the outer fiber of each section. You can see the farthest one apart is this one, so that becomes the C1 for the total section. Here, the farthest one up is this one, that becomes the C1 for the total section. And then you got the S and the SA, okay? So you can go in here, once you get this set up, you get used to using it. And I'll put this on the Blackboard, this spreadsheet, and you can download it. And if you're watching the video, I guess if you want to get a copy of this, you can send me an email, and if I respond, hopefully I'll be able to send it to you. But my email is all right. So you can send it to that email. It's an EDU. And I should send it to you, okay? If I don't send it to you, you can nag me twice. If you send me 3 emails and I don't respond, that means I'm not doing it anymore. But if I don't send you after the first email, you can send me a second email. All right, so now you have I probably should make a new picture here, but I'm a little too lazy to do that. But this will actually give me a way of computing I-beam sections. If I change the the width to 6, you can then see the effect. And the nice thing about this is I can actually change these variables and try to come up with a good effective SA or something like that, S over A. All right? Okay, let me do another one actually while I'm here and show the whole setup again. Let's start over. Let's delete this sheet. Okay, that's fine. Let's show you do for another section. So we have this problem here that we have to do in one of the problems I do online, where we have to compute the I's, actually about both axes, because this is a non-symmetric bending problem, for this C channel, or if you lay it down, we can call it an N channel because it's on its side. So here's the N channel, and the way I'm going to analyze this geometry is basically, I think there's another one here. I think this is the good approach for analyzing the geometry on this one, is we'll take this outer box and subtract the inner box, okay? So here's the calculations here. You can compute the area of each region. The area of the inner region is going to be subtracted, and then here we can find the centroidal locations. Once we do that, we can do all the other calculations, okay? So you can do those by hand, or we can use the spreadsheet. So let's look at how we would use this with the spreadsheet. So there's going to be 2 boxes here, and one's going to be a negative area. All right, so the first section is going to be the outer, and the intersection is going to be the negative area. All right. So the way we would do that then is make a new sheet, and let's just do this for the N channel. Okay. And let's change it to normal layout. Let's just copy all this stuff from here. I won't copy the picture. I don't really need that. That's the same. You get the concept. You can copy it over if you want. But this is no longer going to be an I-beam section. This is going to be an N channel. Or I should do lowercase n, so it looks like that shape. All right, and what are we going to use for the properties of the, we'll have the width. We'll have the width of the N channel, the height of the N channel. Oops, I should delete this. The height of the N channel. Come on. And then it's uniform thickness, so we'll just call this the wall thickness. All right, we'll get rid of this. We don't need this, so we'll just delete that. It'll cause some errors, right? I think, right? You get some undefined here, something like that. But we'll fix that in a second. So this is the wall thickness. Those are the 3 things we need. And in this geometry, for at least for that problem, the width is 200 millimeters. So let's put it all in meters. 0.2 meters. The height is, I'm sorry, the height is 200 millimeters. The width is actually 400 millimeters. And then the thickness is 20 millimeters, 0.02 meters. So that's the wall thickness. So we're going to have 2 boxes. I don't need any tube, right? So let's just delete all this stuff. Or clear it, I guess. Okay. So we just need to have the, this is going to be the outer section, and then, oops, this is going to be the negative intersection. Okay. All right. So the base of the, whoops, the base of the outer section is the width of the N channel. The height of the outer section is actually going to be the height of the total end channel. Now for the negative section, the width, or the base of it, is going to be the total width minus 2 times the wall thickness, right? That's, right, this one here is the width here is the total width minus twice the wall thickness, right? Okay, and likewise the height is going to be the total height minus the wall thickness, just one wall thickness. Okay, and that updates all this stuff. All right, let's put this here. So we're going to use these, and actually I will not need this row, so I can just delete that row. Moves everything up. If you need to add a section, you can insert a row. That's fine. All right, so the YB for both of these is actually 0, right? Because they both lie right on that datum. All right, so that's nice. And then I can just actually just copy and paste here to here. Whoops. Wait. Oh, it shifted the equation. That's why. Let's not do that. Let's just do this. Let's say this is equal to D11, which is what you want. And then this goes to this one, this goes to this one, and this goes to this one. Right? And then we'll do the same for the bottom. Except I think this is wrong. Okay, that was well, that was about a 4-hour break, so I have to remember where I was. Let's finish this up. So, right, so here we're putting in the values for the intersection, right? This is, remember, this is the one that's actually going to be a negative cross section. So, right, it's D12 is the C, and then I can actually just pretty much cut this formula over and get all these guys. Now, the one difference I have to do here, though, is since it's a negative area, I'll pick up for that negative area. You could actually have done it up here, but let's do it in here. Whoops, in here. And so instead of this area being F12, I'm going to make it negative F12 to get the negative area. And now here you can see it gets the correct total area, the difference. And then when it gets the weighted area multiplied by the moment, the first moment, I got a negative value here. All right. And it compensates everything correctly. So the negative areas work fine. Just make sure you put a negative sign in front of the area. Now, okay, so what are we left with? It goes through, again, here's the location of the centroid of the sections. This is the outer section, 0.1 meters. That's half the height, and 0.09 meters. This is the product of the area times the YC. Here's the sum of those. So that's the numerator of the equation for finding the CG. And so here, all we're doing is we're taking that numerator dividing by the total area. And that gives me the location of the centroid. Now here, right, to get, say, the distance between the centroid of the first shape and the neutral axis, it just takes the difference of the centroid from the original datum reference, the bottom edge, right? The difference from this centroid to the bottom edge, and subtracts off it the location of the neutral axis, right? So that gives me the correct value there. You don't have to touch these, right? And then, whoops. And likewise, then computes I parallel axis, and then computes the outer fiber distance for each section, and then picks the max. So all the rest of this stuff you don't have to touch. You really just have to touch these and figure out how to add them together. All right, and so then that gives me, finally, the inertia of that section, 4.08 times 10 to the minus 4th meters to the 4th. The outer fiber distance below, so it's 0.143 meters below the neutral axis, and then to the outer fiber to the top is 0.057 or 57 millimeters to the top, okay? Which is what you would have expected, right? This is 57 millimeters, and this is 142 millimeters, okay? Now, if you wanted to do it for the C channel on its side, it would work the same way. You just have to look at this, but put in the parameters of the rotated section, right? So we would draw this picture, and we could do that again. So actually, if you really wanted to do that, we could probably do that real quick. Let's just cut and paste this. All right. So this will be around its side. So we're going to do this picture. So in fact, the difference here is, let's go back. See if I can get all this onto the one screen. Let's see if I can shoot this over to the side. And we'll move this one over like this. So, okay, it's got all the input parameters. Oops, I got to move it over. Let's paste it here. Okay. No, wait. I should get the whole thing. All right, now we got the whole thing. YB, now the outer shape is still going to have YB at 0. Let's cut C1, C. Let's do this. This is equal to 11. Oh, you know what? I will actually need to make a rotated box. You know, actually, yeah, the easiest way to do that. Let me not do it this way. I'm sorry. Let's delete this. You can't see this, but I'm doing edit clear. Probably the easiest way to do this is just to take this whole measurement cut all this just to all right, so this is what I have up here so far is computing the I for this orientation. So this is giving me the I for bending around the z-axis. Now if we want to look at that shape, the bending around the y-axis, let me just copy this whole thing, do the whole section again. Put a no. This is about the y-axis, and this is about the z-axis. So here we'll have the same boxes, but now I'm going to have to switch the base and the height. This is actually going to be the base of the outer box. Now is what was the width before, right? That's actually going to be the base is this height. Okay, so that's going to be B4. And this is actually going to be B3. Right. The height now is 400 millimeters. And then on the intersection, this is going to be, the base is really just this minus the wall thickness, 0.18, and this is going to be the height minus 2 times the wall thickness. Really just those things flipped. And so this picks it out. Now the IZ, so this is using the IZs instead of the IY. I'm sorry, it's using the I, well, what was the IYs up here, right? You can see this comes to here and these flip. Maybe you can't see because it's off the, these guys have flipped, right? So this is now doing the bending about the y-axis, this orientation. I'll have to shift the base point of the intersection. The base point of the intersection is now no longer at 0. It's actually up the 20 millimeters. So we're going to make that be, it's up the flange thickness, right? So now that shifted that up. And it picked, and now we should have the calculation correct here. So this gives you about the y-axis. So here, as we would expect, the centroid is right in the middle. It's half the height, 200 millimeters. And then this is, in fact, the bending about the y-axis. This is the I for bending about the y-axis. Here's the bending for I about the z-axis, okay? And here are the outer fiber distances. All right? All right. Sorry if there's a big discontinuity there, because like I said, I went out to lunch in the middle of the video, okay? All right. And again, if you want to, I'll put the spreadsheet on WebCT, or if you see this video otherwise and you're interested in the spreadsheet, maybe you can send me an email and I'll try to respond, okay? No guarantees, though.